Okay, hello everyone, and welcome to another Tutte Colloquium. Today we're very lucky to have Laura Mancinska from the Q Math Institute at the University of Copenhagen. As many people here in the audience will know, Laura was a PhD student here at Waterloo a few years ago. She works in various areas of quantum computation and quantum entanglement, and today she's going to be telling us about fixed size schemes for certification of large quantum devices. So please go ahead, Laura.
Yeah, it's my great pleasure to talk to you and kind of be back in Waterloo, even though just virtually. So as Steve said, kind of my main research area is quantum computing and information. So I think about things like what kind of tasks can we accomplish better with these quantum technologies than conventional ones, or address some new challenges that arise when it comes to these quantum computers. This kind of certification task is definitely one of such areas where kind of new challenges arise as compared to the conventional case. And I've structured my talk in kind of two parts. In the first part, I'm going to just try to convey this idea or this problem of certification and also present kind of a mathematical definition. And then in the second part, I want to tell you about a result that we have together with Chris Schaffhauser and Jitendra Prakash, where we show that you can certify arbitrarily large quantum devices with kind of a fixed effort. All right. So in this first part, I'm going to present this idea of self-testing. Perhaps this is not the most descriptive term. So every time you hear me say self-testing, feel free to replace it in your head with something like certification or verification with minimal assumptions. All right. So this self-testing, it seeks to address this fundamental challenge, which asks, given a quantum device, how do we know that it's doing what it's supposed to be doing, right? So imagine that you buy some kind of quantum computer or quantum device, usually comes together with some claims, some specification of what it's supposed to be doing. How do you know that the specification is accurate? And I'm going to be concerned with verification of two kind of elementary functionalities. And you could really see any quantum protocol as being built out of these two functionalities. The first one is production of quantum states. So you could think of this as some sort of box where you press a button and out should come a specific quantum state, right? And we would specify quantum state using a unit vector in some complex space of some dimension d, right? But now, when you press this button, it's not like you see this vector directly. This vector is rather describing the state of some quantum system. Think like maybe photon with a certain polarization, something like that. And this polarization, you can't really see it directly. And this is really one difference between kind of quantum and classical information. The second type of functionality I want to certify is that of quantum measurement. So this would be a box where you put in a quantum state. And in the case when your measurement has two outcomes, it would just produce a bit. So a classical label that's 0 or 1. And mathematically, we would describe this two outcome measurement using two positive semi-definite operators that add up to identity. Okay, so now if you have trusted quantum measurement boxes, so some boxes that you know that they function as they're supposed to, then you can test your quantum state generation boxes by simply kind of pushing this button and performing your trusted measurement and seeing that the outcome is what you expect it to be. Right? And similarly, if you have trusted quantum state generation boxes, then you can test your untrusted measurement boxes. But now in self-testing, we are interested in this scenario where we have a bunch of these boxes, but we don't trust any of them. Okay, so we kind of want to accomplish this certification task in the maximum paranoid scenario where we don't trust any of the devices that we have access to. And if you think about it, at first it might seem that, well, that's just not possible. And of course, because I'm giving this talk, actually, that's not the case, and there is a way to do it. And maybe so what you do here is, rather than just taking one state generation and one measurement box, you take several of these state generation, of these measurement boxes. You give some of them to Alice and some of them to Bob, and then you have only one state generation box, and this generation box is supposed to make a quantum state that is what we call bipartite, so you can distribute it between two agents like Alice and Bob. And then what you want to do is kind of cross-check the answers that the measurement boxes on Alice's side give you against those of Bob's. Right? And this, maybe the idea is somewhat similar of how you would interrogate two witnesses in separate rooms and then cross-check their answers against each other. So even though this self-testing kind of has minimal assumptions, there are still some assumptions that we need to make. One of the assumptions is this no communication. So after you ask Alice and Bob to perform certain measurements, so think of these measurements as being numbered, like measurement number 1, number 2, up to some number n. And so you ask Alice to perform measurement number x and Bob to perform some measurement number y. Then you collect the answers, the measurement outcomes that they got. Right? So you want to enforce no communication between Alice and Bob after you have asked them to perform this measurement number x and y respectively. And another assumption is that we trust quantum mechanics. So we are not in some setting where we are trying to test theories. We assume that quantum mechanics is correct. All right. So what we will do is we will ask Alice and Bob to perform certain measurements. So measurement number x and y, sampled according to some distribution. And we just ask them to respond with the outcomes. And we try to collect kind of these probabilities. Sometimes this P is called correlation. So this is the probability that upon performing measurements x and y, Alice and Bob obtained outcomes A and B, respectively. Right, then a generic self-testing statement, informal version of it, would say something like this. So it would say that essentially there is just one way for Alice and Bob to produce this specific correlation P, or this joint conditional probability distribution P, and that is by performing some specific measurements for Alice and Bob on some specific state, psi, right? So then kind of the big picture idea is that if you observe these probabilities P, then you know that the state generation box you use to produce this psi is actually producing the state psi that you wanted to. And these measurement boxes are performing these specific measurements that you wanted to. Okay. So this would be called self-testing or certification from a correlation, because maybe to prove this statement, you actually need to know all of these probabilities P. But sometimes you don't need to know all of them, and it suffices to just know the value of some linear functional evaluated on this probability vector P. Okay. And this is the case, for instance, in the case of so-called CHSH game that is often used in quantum information. So here, each of Alice and Bob, they just have two measurements. And the outcomes for these measurements are binary. So these labels X, Y, A, and B, we can think of them as being bits, taking values 0 and 1. And then what they're trying to do is they're trying to answer with A and B so that the XOR of A and B is equal to the product of the inputs X and Y. And if you enforce this no communication between Alice and Bob, then you can show that using quantum mechanics, there's some maximum probability with which Alice and Bob can satisfy this condition. I would refer to this as the optimal success probability in the CHSH game. In this case, an informal self-testing statement would say that there's essentially just one way for Alice and Bob to hit this maximum success probability, and that is by performing these specific measurements on this specific bipartite state. Okay. Now, when it comes to real world, there's one problem with these statements that I showed you, and that is that these statements are not robust to error. So for all practical purposes, what we want are robust self-testing statements. And the reason why we want these robust statements is kind of twofold. One is that whenever you build some actual devices, they will experience some level of noise. Right? So you will never get this optimal success probability or this exact correlation. Another source of error is that we actually don't have knowledge of this exact success probability or exact correlation. All we can do is we can sample many times to estimate these quantities, right? These probabilities or this success probability. So we will always have some error due to finite sampling. All right. So in practice, what we're after are these robust self-testing statements. And in case of CHSH, it would say something like this. So it would not only make statements about what happens, what is the state and measurements if you hit this maximum optimal success probability exactly, but it would also give you guarantees of what state must have been measured with what measurements in the case where you're only close to this optimal success probability. Okay, so it would say that, well, if you want to reach near optimal success in the CHSH game, then actually you still need to measure a state that is close to this ideal state with these measurements that are close to the ideal ones. Okay. All right, now what I want to do is kind of move towards a mathematical definition of certification. And our problem so far is this word essentially. Okay? So that's what I'm now going to try to clarify. To what degree can we, is this state and measurements unique? Now let's look at this setting, okay, where Alice and Bob perform some measurements on some shared state. Now a strategy for doing it consists of Alice and Bob picking some state and then picking these measurements, right? Maybe we don't know what this state or what these measurements are yet. And now, if Alice and Bob measure this specific state using these measurements, and quantum mechanics tells us that, well, we can compute the probability that they get outcomes A and B upon performing measurement number X on Alice and measurement number Y on Bob, according to this formula. Okay. So now, if there is some other strategy, say S, for which these numbers, these probabilities are the same as for S tilde, well, then there's no way we can distinguish between S and S tilde, because all we have access to are these probabilities, in a sense, right? We don't know what is the state and what are the measurements. Okay. We just see these probabilities. And actually, there are kind of two general transformations that we can apply to any strategy S tilde that will go unnoticed at the level of these probabilities P tilde. Now, one transformation that you can do is you can apply some local unitaries, or more generally isometries, U tensor V on Alice and Bob, and then you can kind of undo them on your measurements. So when you plug in kind of this new state and new measurements in this formula, these isometries are just going to cancel out. They're just going to give you identities, right? So you will get the same probabilities from this strategy as you did from S tilde. Another thing that you can do is you can take your shared state and you can tensor it with some other unit vector. And then kind of operationally speaking, what you do is you do nothing on this additional state. Mathematically, what that corresponds to is you tensor on identities on your operators. Okay, and again, if you plug in this new state and new operators in this formula, you see that it evaluates to the same thing as here, right? So you cannot distinguish between S tilde or some strategy where you have modified this S tilde in these two different ways. And this basically motivates the mathematical form of the definition of certification. Okay, so here we start with two strategies, S tilde and S. So a strategy is a triple, so it consists of this bipartite state, so a vector in some tensor product space, and then the measurements for Alice and Bob. Okay. You have S tilde and S, two strategies. Right now we can say that S tilde is a local dilation of S and denote it using this embedding symbol. If we can find a local unitary or a local isometry, so some U tensor V, that maps this state psi from strategy S to this state psi tilde from strategy S tilde, potentially tensored with some auxiliary state. But not only that has to hold, but actually the same kind of equation has to hold if you have applied these measurement operators on your state psi as well. So we're asking for existence of this local isometry U tensor V, and then this auxiliary state psi aux. And then we say that S tilde is a local dilation of S. And then we're going to say that correlation P tilde self-test S tilde. If whenever you have an arbitrary strategy S that gives rise to the same P tilde, then you can obtain S tilde by locally dilating this strategy S. Okay. So for every S that gives rise to the same probability distribution, you can kind of extract this S tilde using appropriate local isometry. All right, maybe let me make a few remarks about the definition. So first of all, so I have two of these equations. Actually, equation 2 is strictly stronger than equation 1 because remember that my measurement operators, they need to add up to identity. So if I fix X and Y and I sum over A and B, then I'm going to get identity here and identity here, which is going to recover this equation 1. The reason why I have both of them is that sometimes people just prove this first equation, okay, and then that would be referred to as self-testing or certification of the state. Whereas in the second case, we would say that we are certifying or self-testing both the state and the measurements. All right. And then there's also some physical interpretation of kind of these equations, and what it's saying is that there's some kind of local processing or change of basis you can apply to the devices at hand that will then give rise to this canonical or ideal functionality encapsulated in this kind of strategy S tilde. All right. Okay. And remember, I mentioned that, well, from practical perspective, we care about the robust version of self-testing, right? so now to define that, we kind of relax all these equalities to approximate equalities, all right? So we would say that S tilde is a local epsilon dilation of S, and denote it in a similar way, just putting this epsilon on the arrow, if this equality holds up to epsilon, right? Now these are just vectors on the left and right hand side. So when I write this approximate sub epsilon, what I mean is that the say 2 norm of the difference of two vectors is upper bounded by epsilon. All right, and now we would say that correlation P tilde robustly self-tests S tilde. So in other words, observing this P tilde allows me to certify the states and measurements from S tilde. If for every epsilon, think of epsilon as kind of the desired closeness to ideal of your measurements and of your measurement and state generation boxes, we can identify a delta so that whenever you have a strategy that produces a correlation that is delta close to this ideal one, this P tilde, then you know that you can epsilon dilate S to S tilde. Okay. So you have these two parameters, epsilon and delta. So epsilon is how close I want, what guarantees I want on the boxes that I have at hand on these quantum devices. And delta is my requirement of how close this correlation that I observe has to be to this ideal. Right, and ideally we actually want an explicit dependence between epsilon and delta, and more generally we might want this dependence to be nice, something like square, not exponential. Okay, and depending on the kind of perspective of people working on this self-testing, so there's kind of maybe two bigger communities, different communities working on it. One would be more from physics perspective, and another one would be more from computer science perspective. And then in case of computer scientists, they are often happy just kind of not caring about constants and rather expressing things in terms of some big O's and so on. Whereas in physics, some people are very focused on kind of identifying the exact dependence between this epsilon and delta and finding kind of the best constants. Because if you want to apply it to some real world experiment, right, you have some finite dimension and you have some finite errors. So you really, if you just have some big O statement, it might say nothing about kind of some system in a lab. Okay. All right. So this kind of finishes the first part where I wanted to introduce the idea of certification and self-testing and also show you the mathematical definition. So if there are some questions about that, then I think this is a good time. All right, so maybe one out of two options, right? Either everything is clear or I've managed to lose everyone. Okay, but now I'm going to switch gears a little bit and rather talk about sort of how efficiently can we certify these quantum systems. All right, so maybe let's at first think about certification of these state generation boxes. A question you might want to ask is, well, if I want to certify a state that has dimension D, how small, what is the minimum number of measurements and outcomes that I need to certify states in dimension D? Will this necessarily have to scale with D? And if yes, then in what manner? Can I get polynomial scaling only? Can I only hope for polynomial scaling, or can I always do it with logarithmic one? And so on. So questions like this. And because of how kind of quantum systems scale, in order to be efficient, I actually want the scaling to be polynomial in the logarithm of the dimension, okay, not just polynomial in the dimension. All right, so what is known about what can be self-tested and how efficiently, right? This is just some very high-level overview. I'm by no means listing all existing self-testing results. There would not be enough time in this talk for me to do that. So when it comes to measurements, we don't know so much. We know how to certify measurements in small dimensions or measurements of some specific kind. All right. Now, when it comes to states, we are in much better shape. We know that every state, every bipartite state that can in principle be certified, actually can't. We know how to do it, right? And how to do it robustly. And this general scheme that we have, that uses 3 measurements. So see, this number of measurements is independent of the dimension of the state that you want to certify. But the number of outcomes does scale linearly with the number of, with the dimension of the state. Okay? So this number of outcomes, that would not be efficient with respect to the dimension, because it scales with the dimension rather than logarithm. Now, when it comes to kind of more specific states, we can do better. And in particular for maximally entangled states, we know how to self-test them using logarithmic number of both measurements and outcomes. Okay, but then just a couple of years back came this very surprising result of Honghao Fu, who actually also used to be in Waterloo. So he showed that it's not necessary for the number of measurements and outcomes to scale with the size of the dimension, right, of your quantum system. So he showed that there is a family of so-called maximally entangled states. And in this infinite family, it's not every maximally entangled state that he could self-test, but there was a sequence, a growing sequence, infinitely growing sequence of these dimensions, where he showed that you can self-test them using a constant number of measurement settings. In his scheme, so the scheme is rather involved. In his scheme, he needed about 100 questions. So we show a somewhat similar result. So again, we're saying there are some states and measurements in arbitrarily large dimension that you can certify with constant effort. In contrast to Honghao's result, we can reduce this number of measurements from 100 down to 4. And that's why we also get kind of like a simpler to explain scheme in a way. And another difference is that we can not only self-test states, but we can also self-test measurements in arbitrarily large dimension. Now, there are also some disadvantages of our result when as compared to Honghao's. I think the major one is that for us, in the robust self-testing statement that we obtain, the epsilon delta dependence is not explicit. So we show a statement that says, for every epsilon, there exists delta. Whereas in Honghao's work, this dependence is explicit and polynomial. Maybe this is a good point to mention that although originally kind of these self-testing statements, they came with this motivation of certification. So the goal was to show that some quantum system is behaving as it's supposed to, or that there's just one way to achieve certain success probability or correlation. Increasingly, the self-testing has been used as a proof technique to achieve some bigger result. So it's just kind of one part in your overall proof. Perhaps one of the best examples here is this recent resolution of Const embedding problem using games and quantum complexity theory. So there's a component where you need to prove some self-testing result. Okay, so what I want to do in this, in the remaining time, is to show you some proof ideas of how do we obtain this result. How can we certify these arbitrarily large quantum states and measurements using a constant number of measurements and with constant number of outcomes each. So what we're going to do is we're going to construct an infinite family of correlations, p tilde. So we will, these p tilde, they will have two parameters. The first one is n, and that will take values in natural numbers. And for every n, we will have some family of good x's. Okay, so this x for us, that will be some rational number. And each n will have an enumerable and usually infinite number of good x's attached to it. Okay, so how do we get these correlations? The basic object that we look at is our n projections. And we ask that these n projections, they add up to something that is proportional to identity, and the proportionality constant is x. Okay, so this is where my two parameters come from. N is the number of projections and x is this proportionality coefficient. Now, if you just pick your favorite natural number and some rational x, you're not guaranteed that these projections will exist. But for certain nice pairs n, x, they do exist. For example, let me show you one construction. Okay, so if we consider n vectors in dimension that's one less than the number of vectors, and we take these vectors and they space them out as equally as possible. Okay, so for instance, for n equals 3, right, we are looking at dimension 3 minus 1, that's 2. So in a plane, we space out 3 vectors, we get this kind of Mercedes sign type of construction, right? So more generally, what you get is this regular n simplex. Now, if you consider the projections onto these vectors and you add them all up, well, because they are so symmetrically spaced, what you get is something that's proportional to identity. And the proportionality coefficient turns out to be this n over n minus 1, and that's your x. All right. Remember I said that if you just pick arbitrary pair n, x, you will probably not be even able to find these projections. Now, luckily for us, there is these 3 Ukrainian authors, they have actually classified which are these good pairs n, x when you can find these projections. Okay, so for every n, they identify the set gamma n consisting of these scalars, these proportionality coefficients x, such that this equation can be satisfied. First, you can find some projections satisfying this equation. Not only they did that, they went one step further, and they also identified a subset of these sets gamma n. And this is, in this subset, the choice of these projections is essentially unique. So what it means that there's just single irreducible representation kind of for this equation. Okay. So whenever you have some pi's that add up to this x times identity, then they are arising as identity tensor, this irreducible representation, pi tildes. So what we will be concerned with is kind of this very nice set, this lambda n, where you also get this uniqueness of irreducible representation. All right, now we need to get correlations somehow, right? All we have so far are these n projections. So we take this pair n, x, so n at least 3. Oh, maybe one thing I want to note about, want to say about this set lambda n is that, so for n equals 3, it's finite, But then for all higher n's, it's enumerable and infinite. Okay, right. So how do we get to correlation? So we take any n, at least 3, and then we take x's from these sets lambda n identified in this paper I mentioned before. And we look at a strategy first. So a state together with measurements. So the state that we take is this maximally entangled state, defined like so, in the same dimension as this irreducible representation corresponding to that pair n comma x. And how do I get measurements? Well, they will just be 2 outcome measurements. So from every projection, I'm going to get a 2 outcome measurement by simply taking 2 operators. So I take this projection and then identity minus that projection. Okay. Remember the requirement for being a quantum measurement, I needed positive semi-definite operators that add up to identity. And I have that, right, by construction. Right, and then the correlation is simply, the correlations that we look at are simply the ones given by measuring this maximally entangled state with these n2 outcome measurements. Okay. And then the theorem that we get is that these correlations p tilde nx, for when I take n at least 3 and x to be in this nice set lambda sub n, then these correlations, they certify this strategy S tilde. So they certify the presence of this maximally entangled state and of these measurements that I got from this irreducible representation. Okay. And this is just if I write out the theorem statement, including all the definitions, kind of essentially the definition of what it means to robustly self-test. But as I said, like the definition of robust self-testing that we are using is this, that for every epsilon there exists delta, okay? And kind of in the ideal world, what you would want is explicit dependence between this epsilon and delta. All right, so how do we achieve this robust self-test? And I'm just going to show you kind of the structure of the proof. So in general, when it comes to self-testing proofs, kind of one thing that I don't like about them is that they seem to follow some ad hoc approach. So it seems every time you want to prove a new self-testing result, you kind of have to start from scratch. Now there is one nice exception to that. And that applies to cases where you can identify an underlying group to your setup, to your correlation, or to your game. Okay, and it's not always possible to identify this group, and it's not clear even what this group should be necessarily. Okay, but this proof strategy, this general proof strategy proceeds as follows: if you can identify this group, and then show that near optimal strategies, so strategies that either reach this reach success probability close to the optimal one, or produce a correlation near to the optimal one, they somehow, these strategies, they lead to approximate representations of this group. Okay, so they're not quite representations, but they satisfy this defining relation of being a group representation approximately. Okay, and then finally, to kind of get your self-testing statement, you apply this Gauer's Hatami theorem that essentially allows you to take an approximate representation and identify an exact group representation nearby. All right. So this is very nice because this kind of proof approach is general. As long as you can identify the group, you can kind of think that you can accomplish the proof. All right. Now, as I said, you cannot always identify a group. Well, I think you cannot always identify a group. However, if you look at the existing self-testing proofs, it seems that practically all the proofs I know reduce to showing that reduced to some kind of algebraic relations. Okay, so we might want to perhaps try to generalize this proof approach to where we don't need to identify a group, but it's enough to identify an algebra. And this is what we follow, but this is the approach that we follow, but in this specific case of these projections that add up to identity, to something that's proportional to identity. Okay, so we need to identify an algebra. In our case, remember we started with these projections. So we say, okay, we take the algebra generated by n projections. So this is this projection requirement. And then we say that they add up, these projections need to add up to this x times identity. Okay? And for our nice pairs n comma x, we look at this algebra generated by these n projections with these relations. Okay, and then the next step that we want to do is similar as here, right? So we want to show that near optimal strategies lead to approximate representations of this algebra. And then the last step, which is the most problematic one, is that we need some analog of Gauss Hatami. And in general, I'm not aware of any such statement in the case of algebras. What I want to mention here in this step 2, that it's very important to choose the right definition of approximate representation. Okay, so people who study algebras and stability relations, they kind of look at similar questions, like for that would lead to kind of similar statements of Gauss, to statements similar to Gauss Hatami, but for algebras. But oftentimes the notion of closeness or proximity is with respect to a different norm than what's useful in the case of these certification results. Okay, so what is a good notion of approximate that we know how to leverage in this context of certification? So let's consider a list of polynomial equations in some non-commutative variables, x1 up to xn, and their adjoints. Okay. So I have k equations. All right. Now, what does it mean that I have an approximate representation of these k equations? Now, my approximate representation will have two parameters, delta and sigma. Okay, delta says how close am I to satisfying these equations exactly, and sigma will have to do with how I'm measuring my norm. Okay, so what I'm saying is that for a given delta and a density matrix sigma, so this would be a positive semi-definite matrix with trace 1. We're going to say that a list of matrices x1 to xn, they form this delta sigma representation for this list of polynomials if the sigma norm of each of these equations is upper bounded by delta. Okay, so if it was kind of exactly satisfying these equations, then I would have 0 here. Like inside here, I would evaluate to 0. But now I'm allowing some approximate representation, and that's where delta comes in. Right now, what is the sigma norm? Well, essentially, I'm just scaling the norm of this x by this sigma. Okay, and remember, sigma, you can think of sigma as some positive semi-definite operator with trace 1. Okay, so maybe a diagonal operator. with entries that are some probabilities. Okay. Right. So this is the notion of approximate representation that we want to use in this context. And now we kind of, we need to find some way to deal with this non-existence of Gowers' Hatami theorem in case of algebras. And we deal with it in case of these specific algebras P and X. But maybe first let me show you how the statement of Gowers' Hatami theorem looks like, and then I'll show you what our analog is. This is my most technical slide, and then after that, I'm just going to summarize what we've shown. All right, so Gowers' Hatami applies for finite groups. So we have a finite group G, and then we have some dimension R and some epsilon. So epsilon is now this how close to being an exact representation you are. And again, you have some sigma, which is a density matrix that you will use to define your norm. And then you have tau prime, which is this approximate representation of your group. So it maps group elements to unitaries in this dimension R. What Gowers' Hatami tells you is that you can always find an exact representation, tau, right? Where you can see this tau prime as arising from a corner of this, this exact representation, tau. So what this V star V does, in essence, it kind of picks out some corner from your exact representation. And you moreover know that there's a very nice estimate on how close these two objects are, this corner, how close this corner is to this approximate representation. See, it only depends on the size of the group, and it depends on the quality of your initial representation, but it does not depend on R, right? On this dimension in which your approximate representation was in. So that's very
question, Laura?
Yeah.
So here, this epsilon sigma representation, that's with respect to the relations that define the group, like the relations amongst its generators. Is that how it goes?
So the way that this representation is defined in the group case, it's more like an average over the whole group. So it's average over a group. There, the group is not necessarily defined as generators with relations.
Sorry, so what does it mean? So can you give an analog of the definition that you just previously gave in terms of polynomial relations? Like, you know, how does? So
I think actually this group, this definition in case of groups, it is somewhat different than how we define it for algebra, like what I showed you, because there we require kind of closeness on average over the whole group. So you would say take the expectation. So if you have a group representation, right, what you want, say your group representation is tau, you want that tau of x times y is equal to tau of x times tau of y, right? That's how you would define that something is a representation. And now you could just take the expectation over this xy and ask how far off am I from the difference between tau xy minus tau of x times tau of y being 0. Now, if I had an exact representation, this expectation would evaluate to 0, but I'm now requiring that it's at most epsilon.
Thank you.
So somehow in the case of algebras, you could say that I'm starting maybe from something slightly weaker because I'm only requiring that on these generators, right? I'm close, like that these relations on generators are satisfied up to epsilon. But somehow if I now start to generate some longer words in my algebra, sort of the requirements I have on those are more lax, right? Yeah. Okay. So the analog in our case, and as Ashwin kind of pointed out, or Ashwin's question pointed out, I mean, there are some things I'm sweeping under the carpet, like I'm not, maybe this definition of the representation in case of a group is, as opposed to the one that I'm asking for algebras, it's not clear that it's exactly analogous. Right? It's quite natural to define it this way, but there are some differences. Okay, so first of all, we don't prove this analog for general algebras. We only prove it for these algebras P and X, where N is a natural number and then X comes from this nice set. Okay. So what we show is that for any epsilon, we can find a delta and an M, such that if you have a list, so remember this algebra P and X, it was generated by N projections where you added up to X times identity. So think of these E's as being assigned to these kind of abstract generators. You have these E's that will give your approximate representation. You have this density matrix. And then we have two requirements. So first one is that this E1 up to En, they form this delta sigma representation of the relations in P and X. And these relations were just projections and this adding up to X times identity. And then the second requirement is that this state is kind of approximately tracial on words and words that are not too long. So they have degree at most M in these variables E1 up to En. Okay. So this second requirement is not present, for instance, in Gowers Hatami. Okay, and there's only the first one. Then the conclusion that we get is very similar to the one in Gowers Hatami. You see, we are saying that these EIs, right, these objects that give us our approximate representation, they are close to being corners in an exact representation. Okay, but because in our case, we only work with these pairs N, X, where there is a unique irreducible representation, then I actually know what that representation is, like how that exact representation, how this tau, right, in Gowers Hatami case, how it can look. It's just this irreducible representation tensored with identity of some size. Okay. All right, kind of the downside, and this is where our non-explicit epsilon delta dependence comes from, is precisely this analog of Gowers Hatami, because we can only show that for every epsilon there exists delta, whereas in Gowers Hatami this relation between epsilon and delta is explicit and it's square. Okay, so let me just summarize kind of the main theorem and this main result in the second part. And the implications. So what we did is we started by looking at these projections that add up to something that's proportional to identity. And then from these projections, we defined some correlations. And these correlations, we showed that they self-test these maximally entangled states in that maximally entangled states, and these measurements that we obtain from this unique irreducible representation of this relation. Okay. All right, and now to kind of get this form of the theorem that I showed you much earlier, we actually just focus on one fixed n. We take n equals 4. Okay, in general, these x's in these sets lambda n, they are obtained using some recursive formula. And at least I'm not aware of how to get an explicit form of these x's in these sets lambda sub n in general. However, when n is equal to 4, things become simpler and you can understand precisely how these x's look like. And they take the form of 4k over 2k plus 1. And it happens that this irreducible representation is always in the dimension. So if you look at x, then you need to look at the denominator for this x, and that is the dimension of your irreducible representation. So for us, it's this 2k plus 1. Okay, so then the strategy that we build out of these projections, it will be in dimension 2k plus 1. But now, what does this strategy consist of, right? So n is equal to 4, so we will have 4 two-outcome measurements. But this dimension, 2k plus 1, that grows to infinity. So it tells, like, just these correlations, so this 4 comma x, they are of constant size, but they will allow you to robustly certify maximally entangled states in growing dimension along with those projections. And that's how we get this family of constant size correlations that are capable of certifying arbitrarily large states and measurements. Maybe one thing that I want to stress again is that kind of just, we don't give a scheme to certify arbitrary states in arbitrary dimension using constant effort. We just show that there exist states of arbitrarily large dimension that can be certified using constant effort. And this first question that I mentioned, that is open. We don't know whether or how we can certify an arbitrary state in arbitrarily large dimension using constant effort. Okay, so that's all I wanted to tell you today. I guess I went a little bit over time, but maybe we can still have a question.
That's okay. Let's thank Laura for a great talk. Are there questions? I guess one question I had is, so you mentioned for general n, these lambda n's are defined by recurrences. What form is the recurrence, or what type of recurrences?
I won't be able to tell you on top of my head. So you just look at the one previous term. So like to get, say, xk plus 1, you just define it from xk. Then there's some relatively simple formula involving this xk and n. Okay. But I don't think none of standard methods, at least that I know of, how to solve recurrences would give you this closed form.
Okay, thanks. Ashwin, you have a question?
Yes. So let's say I took your theorem to sort of quite literally, or the statement, this final statement quite literally. And in a lab, I wanted to verify whether a certain entangled state was, your chosen state with parameter k. How many? So basically, I'd have to measure the state many, many times in order to ensure, first of all, that the correlations I obtain are close to the ideal one, right? So your the closeness parameter, I forget whether it was epsilon, and it was sort of related to various other dimensions, or maybe size of the group and so on. So so to verify state of dimension 2k plus 1, how many such measurements do you need?
Okay. First of all, I'm gonna try to answer, but let me know if I'm answering the wrong question. So the number of the number of different measurements you will need is just 4, but you will need to repeat, right? You will need to repeat.
Exactly. So the question is, how many repetitions do you need in order to get a sufficiently accurate estimate of the correlations for the state that you actually have, to ensure that the actual state is close to the ideal state with, let's say, up to distance delta.
Right. So somehow the theorem, because of this non-explicit epsilon delta dependence, right? That's kind of, I can tell you that it's not that's the problem with the non-explicit epsilon delta dependence, that I won't be able to give you specific numbers. So this is more of a theoretical result. Like, we think that actually there is an explicit epsilon delta dependence that could be shown. But in general, kind of also self-testing results often, they kind of just start by assuming, oh, I have something that produces a fixed correlation or achieves gain value of something. And then to go and apply it actually in the lab, you kind of have to put this another layer on top that deals with this sampling kind of issues of sampling. And it's kind of a separate layer, but that is common to all self-testing results.
Yes, of course. Yes, yes. So I guess in order to head towards that direction, one would have to characterize the the closeness of your observations to the ideal correlations, right? And
yes.
How that translates to closeness in the strategies and actually the state. I mean, I guess finally it's just the entangled state that you're interested in.
Yes, so there are kind of two things, and I'm saying, one, we don't know how to do, and we don't know yet how to do for this specific scheme I presented, because we have this non-explicit epsilon delta dependence. So it's in principle unclear to me, like how to get there. And then there is this other issue, like that is kind of common to all self-testing results, that on top of them you need to put this other layer, which will tell you how many times you need to sample, and there will be like another parameter, right, that says like, oh, with small probability, like with overwhelming probability, the measurement you actually did must give you this success probability. Right? If you need to sample enough times to gain good enough confidence.
Right.
And that's, I think, somehow we don't deal with it. Usually self-testing results don't deal with it, but that's a common layer that needs to be put on.
I also want to follow up with a question here that Hong Hao's result has explicit epsilon delta provided.
Yeah, yes, exactly. That's like, I think, a major advantage of Hong Hao's result over ours.
Interesting, because the embezzlement direction to certify large states, it doesn't actually do self-testing. It actually has fixed system size. Again, you can verify embezzlement with better and better accuracy. So it implicitly verifies one out of the many possible embezzlement states, but you cannot specify which embezzlement scheme has been used. so all these approaches have some problem because the embezzlement has also very, very few measurement. It's very easy to repeat, but it doesn't actually do self-testing. So.
Okay, William, you have a question?
Oh, yeah. Hold on, here we go. So really enjoyed the talk. We were just reading over the last couple of months your paper about definitions of self-testing with the operational environment for self-testing. And I kind of, I guess an interesting idea that you have in the paper, some different types of definitions of self-testing from the one you gave here, including some that I guess are actually not just equivalent, but actually different definitions. Do you think, like, is there, when it comes to trying to efficiently self-test certain systems, do you think, could there be different definitions of self-testing that give like different answers for how efficiently you can self-test things? Or do you think if you took some other definition of self-testing that you would get like similar results?
Good question. I think it's a good question. I'm not going to put my money on either of the answers. But maybe one thing I want to say about the self-testing definition is that I'm not convinced that the definition I showed you is the right definition of self-testing.
We're on the same page on that, I think.
Yes, but again, like self-testing definition in the paper you mentioned, I think suffers from some other problems. For instance, so this paper, to be fair and give credit where credit is due, is Nicolas' PhD project. Mm-hmm. So it's him who did most of the work there. But in my opinion, the problem with that definition is that although it gives you kind of a nice theory, I'm not like Nicolas wasn't able to get some new explicit self-tests using that definition, right? So that's kind of, how to say, it's a nice definition maybe to build theories, but like when it comes to proving actual self-tests, at least I'm not convinced yet of how useful it can be in that setting.
Right. Like, so the local simulation is the one that's equivalent to the one you gave from that paper, right? And there's also
under some assumptions, right? Of like Schmidt ranks and
I guess
and projectivity and so on.
Yeah. And maybe the other local assisted simulation and one that he gives is maybe too far from local simulation, but it seems like there could be some others that are close but a little different than the one you gave. But I guess nothing is known about how these change this type of self-testing result that you're talking about today. Is that right?
Yeah. I'm not aware.
Yeah. Okay. Thanks. Yeah.
Okay, great. Let's thank Laura again for her talk.
Thank you all very much. It was really nice to see, even though briefly, some familiar faces. Hi, Debbie.